In Professor Carlos Frank's remark, "I've spent my life at Durham University, an entire life forming a particular perspective on the world, and now that idea is being questioned. Because it is, I welcome it. This is how science advances." James Webb is reversing almost all that was known to be true in cosmology for the last century. A brand new ultra-deep image depicts the progress we've made, and the errors in astronomy. The telescope, which was going to show us the first stars of the universe, is destroying the prior worldview and may usher us into a new science. Many researchers are not afraid at all. Researchers who are impacted by the new information welcome the advancements because it's been clear for a long time that there was a problem with our previous hypotheses. Contradictions in measuring the rate of expansion of the universe should have awakened academics earlier. Rather than correctly interpreting the clues, they missed them due to outdated notions. The cosmic microwave background radiation, CMBR, is thought to be the oldest light in the universe. The CMBR was formed around 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to form stable hydrogen atoms. Researchers refer to this transformation as reionization, which made the universe permeable to light. The CMBR was discovered in 1964 by American physicists Arno Penzias and Robert Wilson while developing a new type of antenna. A constant noise was approaching. They heard it coming from the sky in every direction. This discovery was widely accepted as one of the most compelling pieces of evidence supporting the Big Bang theory. Penzias and Wilson shared the Nobel Prize and secured the CMB's place in astrophysics history. The CMB most probably provides us with a glimpse of the young universe. Tiny temperature changes provide significant information about the circumstances in the universe shortly after the Big Bang. Scientists have measured the universe's expansion rate and other factors using the CMB. Edwin Hubble, an astronomer, had already computed this amount in the late 1920s. Hubble discovered that distant galaxies move away from us in all directions at speeds proportional to their distance. Today we refer to these measurements as the Hubble law or the Hubble constant. Of course, Hubble did not possess the advanced methods of measurement employed decades later. When the CMB was discovered, researchers recalculated the expansion rate, and the new figure was substantially lower than Hubble's initial estimate. Subsequent research recalculated the rate with the help of type Ia supernovae. Like regular candles, astronomers had access to such stable points of measurement. The discrepancy in determining the universe's expansion rate has existed since the 1990s. Since then, researchers have been aware, or, to be more precise, suspected, that there was a problem with our evaluation of measurement techniques or even with the very concept of cosmic expansion. The so-called Hubble tension, also known simply as tension, is the difference between various measurements of the universe's rate of expansion. It has far-reaching repercussions beyond a simple measurement discrepancy. Numerous discoveries reveal significant insights into how we have previously misunderstood the universe. For a long time, scientists were at a loss. Since its inception, the James Webb Space Telescope has given scientists unanticipated results, which may now shed light on the conundrum of the universe's expansion rate. Galaxies that are so mature and old that their origin must have occurred before the Big Bang are entirely at odds with conventional science and astrophysics. There is no longer talk of simply measuring. Instead, academics are discussing the most serious problem in modern astronomy. Not only has the potential to be the universe's rate of expansion incorrect, but the entire idea of expansion, or even the Big Bang itself, is being examined. The photos from Webb show evidence of a universe that is very different from what we believed for a long time. The tension served as an early warning, and now all researchers who continue to believe in outdated theories are being put to the test. Right now, we must ask ourselves, do we actually know anything about the universe? Many scientists are now standing on the rubble of their life's work, staring into space in hopelessness, unable to comprehend what they are recognizing. In light of the current scientific dilemma, we must ask ourselves, what do we truly comprehend about the universe? To address this inquiry, we must first comprehend how science works. Theoretical scientists employ a complicated network of mathematical representations of actual data and deductive reasoning to reach conclusions, ranging from the general to the specific. Their expertise is based on a combination of observed events, extensive experimental data, and theoretical analysis. The name theory alone indicates that these are creations and ideas, not reality. We only have knowledge of the real world in the form of images from telescopes, sound waves, and radiation captured by radio telescopes, as well as the most recent information from neutrino measuring systems or detectors for gravitational waves. With the James Webb Space Telescope, We now possess a tool that allows us to begin breaking down earlier models into their own distinct frequencies and conduct analyses in ways that were previously impossible. Webb can demonstrate what was once impossible. Which elements were prevalent in galaxies over 13 billion years ago? How much mass they contained? How many stars existed? This indicates that the telescope can reconstruct a galaxy's shape and direction of travel. However, Webb may encounter issues in some of its photographs. Due to massive accretion disks, the telescope cannot always distinguish whether we are looking at black holes or galaxies that shine brightly as galaxies. We must confront the fact that our science has long accepted too many possible outcomes as facts without considering alternative explanations. Research has long been misled, despite its truthful intent. Most recent information from James Webb gives important clues for replacing ideas with new truths, as has occurred numerous times in science. Scientists are currently awaiting new results. The data are far too bizarre, and for many, it appears impossible to generate novel interpretations. Right now, the new discoveries are challenging the very foundations of modern physics, which scares many scientists. Today's majority of physics classes are based on 17th-century discoveries made by Isaac Newton. For centuries, his principles of motion and gravity served as the cornerstone of our physical comprehension of the universe. Newton's theories explained the movement of objects under normal conditions and worked well on Earth. However, in space, his concepts required expansion, something Albert Einstein substantially accomplished at the turn of the 20th century. Einstein's special relativity theory, published in 1905, changed our perspective on space and time. He demonstrated that space and time are interrelated and depend on the movement of the observer. His general theory of relativity, published in 1915, developed this idea further by providing mathematical evidence of gravitational phenomena based on spacetime's curvature due to massive objects like stars or galaxies. Einstein's theories were generally cohesive, but he was aware of their limitations. Throughout his life, he knew that. Today, more than ever before, the future of cosmology stands on unstable ground, caught between the crumbling edifice of old theories and the dazzling, terrifying potential of a new, unknown reality. Scientists, rather than retreating in fear, must now step into the void, guided not by certainty but by curiosity. If the James Webb Space Telescope, JWST, has proven anything, it is that the universe refuses to conform neatly to human expectations. Its latest images, ancient galaxies impossibly massive, light bending in unexpected ways, structures too mature for their supposed age, force us to confront the possibility that our timeline of cosmic history is fundamentally flawed. Perhaps the universe was not born in a singular fiery explosion but emerged from processes we have yet to imagine. One possibility gaining traction is the steady-state or eternal universe model, a controversial idea suggesting that the cosmos has no true beginning or end but is in a constant state of renewal. In this view, galaxies might continuously form, evolve, and dissolve across unimaginable timescales, without a singular Big Bang to mark a clear beginning. Other scientists are revisiting plasma cosmology, the idea that electromagnetic forces, rather than gravity alone, play a dominant role on cosmic scales. Moreover, the idea of the multiverse, once the domain of science fiction, has become a serious topic of research. If our universe is but one bubble in a vast cosmic foam of countless universes, each with different physical laws, then many of our assumptions about reality are merely local truths, not universal ones. What we once believed to be universal constants may only be environmental accidents specific to our tiny corner of existence. The implications of these emerging theories are staggering. They do not merely adjust small details in our models, they demand a complete reworking of the foundations of physics, astronomy, and even philosophy. If dark matter and dark energy are misinterpretations, if cosmic expansion itself is not what we think, then every calculation and prediction made in the last century may need to be revised, or even discarded. In this sense, the scientific method shows its greatest strength, its willingness to adapt, to correct itself, and to advance not through the protection of dogma but through the embrace of uncertainty. Scientists of the future will need to become explorers again, not just in laboratories but in imagination, daring to propose new frameworks that better fit the chaotic, breathtaking grandeur revealed by our new instruments. As Professor Carlos Frank admitted with humility, welcoming the questioning of everything he thought he knew, so too must all researchers face the uncomfortable truth: we are only beginning to scratch the surface of the universe's secrets. Every answer we have found has only led to deeper and more perplexing questions. And perhaps that is the true beauty of science, not in the comfort of knowing, but in the endless, exhilarating pursuit of understanding a universe far more strange, beautiful, and profound than we ever dared to dream. What is being discussed is that the physical properties of the two dark components have changed over time, which may indicate that we are dealing with something beyond current understanding. The next thing after intelligence-type phenomena to be tested is gravity. This force, which presumably causes attraction or curvature in spacetime due to mass, has yet to be fully demonstrated. Einstein is significantly responsible for the concept of the curvature of space and time, and this has been demonstrated repeatedly. However, we cannot rule out the possibility that gravity has entirely different characteristics than previously thought, or that the force of gravity between objects is caused by a different mechanism. Several values, known as cosmic constants, have been established in modern astrophysics and cosmology over the years. These values are largely dependable because they rarely alter. Calculations have revealed that slight fluctuations in the purported constants bring about new momentum in the universe, allowing us to explain a variety of events without invoking the existence of dark energy. It is also possible that our interpretations of the redshift of light are erroneous, and that we have been measuring incorrect distances within the universe, determining galaxies for decades. Possibly, our beliefs regarding the origin of the universe were likewise erroneous. We may have misinterpreted the background cosmic microwave radiation. There is even the possibility that the universe has no beginning or end. This would challenge the notion of a single point of origin and suggest that the Big Bang theory is incorrect. Despite our advanced technology, we cannot rule out slight errors in the Webb telescope or other observational instruments. In the midst of this crisis, scientists and instrumentation engineers acknowledge that flaws exist. Interpretation and processing of data are critical. The field of cosmology is always open to possibilities. At the moment, it is at a crossroads, where the foundations laid over the course of centuries are being tested by new observations and information from innovative equipment like the James Webb Space Telescope, JWST. Not only do these difficulties raise questions about well-established theories, but they also open new opportunities for comprehension of the cosmos. One of the fundamental principles of contemporary cosmology is the concept of the Big Bang, which proposes that the universe originated from a point that was infinitely dense and has been expanding ever since. This theory has been supported by various lines of evidence, including the cosmic microwave background radiation, CMB, Hubble constant measurements, and the discovery of the spread of galaxies across the universe. 1964 was a pivotal year for the CMB. It provided strong evidence in support of the Big Bang theory, showing a uniform glow of radiation across the horizon, which is thought to be the hot afterglow of a dense universe in its initial state, before becoming transparent so that it could be seen. This radiation has since been studied extensively to understand the geometry, age, and composition of the universe. However, recent observations and measurements, particularly from the JWST, have created significant obstacles to this established framework. The JWST, with its unprecedented sensitivity and resolution, has started to unveil galaxies and phenomena that defy conventional explanations. For instance, the finding of galaxies that seem older than anticipated raises fundamental questions about the timeline of cosmic evolution and the processes leading to the formation of stars and galaxies. Additionally, differences in the measurement of the expansion rate of the universe, known as the Hubble tension, remain despite years of improvement in observational techniques. While CMB-based measurements point to a particular rate of expansion, independent measurements using Type Ia supernovae as standard candles give slightly different results. This discrepancy hints at potential flaws in our understanding of either cosmic distances, dark energy driving the universe's acceleration, dark matter, or both. Dark energy remains a mysterious component of the universe, representing the majority of its content, yet defying direct detection. These enigmatic substances are invoked to explain the observed gravitational effects on galaxies and the accelerated expansion of the universe, respectively. Yet, their precise nature and properties remain elusive, leading to various theoretical and experimental efforts to uncover their identities. In addition to these theoretical challenges, the JWST has provided stunning visual evidence of phenomena that challenge our current knowledge of the history of the universe. Images of faraway galaxies, some formed only a few 100 million years after the Big Bang, suggest a complicated and dynamic early universe with rapid change. This may require new theoretical frameworks to comprehend. The JWST's primary capacity to analyze the spectra of light from these ancient galaxies reveals their chemical compositions, star formation rates, and even the presence of crucial heavy elements necessary for the processes by which planets and life develop. These observations not only enhance our understanding of galaxy formation but also raise intriguing questions about the circumstances under which life could emerge in the universe. Furthermore, the concept of cosmic inflation, which posits a rapid, exponential expansion of the universe immediately after the Big Bang, remains a topic of debate and scrutiny. While inflationary models offer a sophisticated explanation for the observed large-scale structure of the universe and the uniformity of the CMB, alternatives that do not necessitate inflation are actively being pursued to reconcile theoretical discrepancies and observational challenges. Beyond the discipline of theoretical physics, JWST discoveries also have profound implications for our philosophical understanding of the universe. They force us to re-evaluate fundamental concerns about the nature of spacetime and existence itself. If the universe's rate of expansion varies between different epochs or scales, according to some data, it could imply that our cosmic neighborhood is only a small portion of a much larger and more intricate multiverse. Furthermore, the initial observations of distant galaxies and their development over tens of billions of years provide a glimpse back at our cosmic beginnings and future, offering invaluable insights into how galaxies work and evolve. As we delve deeper into these revelations, it becomes increasingly evident that the universe is more complex and dynamic than previously assumed. The implications of these discoveries extend beyond astrophysics, touching on fundamental principles of reality, causality, and even the potential limits of human understanding. New findings suggest that the processes governing galaxy formation, star development, and the distribution of matter may have been underway far earlier than models based on the traditional Big Bang timeline would predict. This early complexity challenges notions about the uniform progression of cosmic structures and demands a reassessment of the conditions under which the first stars and galaxies formed. Moreover, the unexpected maturity of distant galaxies implies that either the mechanisms of early cosmic evolution operated at an accelerated rate or that our current models are missing key variables. These possibilities open up new areas of inquiry regarding the role of dark matter, variations in the laws of physics over time, and the nature of primordial fluctuations. At the same time, the idea of a multiverse, long relegated to the realm of speculative theoretical physics, gains more traction as observational anomalies accumulate. If different regions of spacetime exhibit distinct physical constants or developmental histories, this could suggest that our universe is but one bubble in a vast and varied cosmic ocean. Philosophically, such a scenario challenges anthropocentric assumptions about the uniqueness and centrality of human existence. It compels us to grapple with questions of meaning and purpose in a cosmos that may be fundamentally infinite, varied, and indifferent to human narratives. From a practical standpoint, these revelations demand improvements in our observational technologies, data analysis methodologies, and theoretical frameworks. Instruments like the JWST are just the beginning. Future missions may require even greater precision and the ability to observe deeper into the universe's infancy. Additionally, interdisciplinary collaboration between astrophysicists, quantum physicists, philosophers, and data scientists will become increasingly essential. Understanding the true nature of reality may depend not only on technological advancements but also on the evolution of human thought, pushing the boundaries of interpretation and imagination. In conclusion, we stand at a pivotal moment in human history. The universe is revealing itself in ways that are both exhilarating and humbling. Long-standing theories are being tested, revised, and sometimes overturned. A new era of discovery is upon us, one that promises not just answers to old questions, but the emergence of entirely new questions, questions that may redefine humanity's place in the cosmos for generations to come.